All right, so 2.3 is a section called linear equations. All right, and things that we've hopefully taken a look at to jog our memories a little bit is what our solutions look like. And so in particular, that was the 2.1 notes and video that I asked you to take a look at. We also talked about, these are some common integration techniques that we might need to refresh our brains on. But again, we're going to try and pick a few of these techniques that tend to be used frequently in this class and really focusing on refreshing those skills. And then yesterday, we talked about how to identify and solve separable differential equations. And so today, our question is similar in nature. We're looking at how we can algebraically solve, not separable though, linear differential equations, okay? And so we're going to be looking at a different type of equation today. And tomorrow, we'll look at another type of equation. And so as we move through this week, it would be really valuable to make sure we know how to distinguish the different types and think about which strategies might be most useful where, okay? All right, as I mentioned yesterday, I like to start with a very general overview. So general meaning there's f of x and g of x and h of x and all these functions that are not specific functions, but that if we replace them with functions, we actually almost have a template on how to solve these differential equations, okay? I think that's a little bit different than how it works in a lot of the math classes you've had up until this point. So I do want to make that very explicit that this first page is more about creating a template for ourselves. How do we move through that process? But it's also to help us understand like why the process is the way it is, okay? Now, it does require us at some points to just kind of believe in some things, all right? So for example, today, we're gonna start our discussion with imagining a magical function that will make this process work, all right? But then at the end of our discussion, we'll talk about where this magical function comes from. So let's take a look at this particular differential equation. So observe that a first order differential equation, and we know it's first order because it's that dy dx, okay? If I had y double prime, that would be a second order. If I had y triple prime, that would be a third order. But this dy dx tells us it's a first order differential equation. And it's said to be linear if we have the following. So linear, meaning we're going to have all of these coefficient functions that are only going to be in terms of x. And the first order part, again, comes from that dy dx. Okay, so the linear part is that we have coefficients that are at most in terms of x, okay? Now, like we did yesterday, we're going to sort of think about how life is sometimes easier if coefficients are 1. And so here I notice that I have a sub 1 of x, so some function of x. If I wanted to make this initial coefficient equal to 1, what could I do? How could I get rid of this a sub 1 of x? Yeah, we could divide everything by that a sub 1 of x, right? No matter what that function is, if we divide by it, then that initial coefficient will be 1. And so that's actually where we're going to start our story. We're going to go ahead and divide by a sub 1. So we're going to get dy dx plus a sub 0 of x over a sub 1 of x, y equals, let's say 1 over a sub 1 of x, g of x. Okay. So all we've done is divide everything by a sub 1. And we're going to rename our functions, in particular this one, we're going to rename, and also this fraction, we're going to rename. And we're renaming them, we don't need to rename them when we're in the actual problem, but for generalization, it's nice to rename just so we don't have to keep writing a sub 0 over a sub 1 or g of x over a sub 1, okay? And so when we rewrite this, let's call a sub 0 of x over a sub 1 of x, let's call that p of x. Okay, so this p of x is the same thing as what we got when we divided it away. And we're going to call 1 over a sub 1 of x, g of x, we're just going to call that f of x. All right, so we divided through, we renamed some things, and this is where we're going to start our story for today. Okay, so we have this function, and let me go ahead and copy this. All right, so we start our story here. All right, we've got our dy dx plus p of x, y equals f of x. And what we're going to say is, go with me for the next few minutes, that we're going to have some magical function, okay? In fact, it is so magical, let's use the Greek letter mu, okay? Oops. Magical function. Let's call it mu. Okay. So I bet you didn't know you're going to be learning so much Greek as well, but we use a lot of Greek letters here. So we're going to call this magical function mu. And what we're going to do is we're going to say, what if we had this magical function and we multiplied the entire equation by it? And if we did that, we would get the following: mu of x dy dx plus mu of x p of x y equals mu of x f of x. All right, so I've got this magical function. I multiply everything by it, okay? Now, because we're clever mathematicians, we chose mu, this magical function, to be very special. In fact, it turns out that mu of x times p of x actually is mu prime of x. Okay, so we've got this magical function, we multiply it through, and we've chosen this function so cleverly that this large piece right here is actually the same as the derivative of our magical function. Now, if we replace mu of x, p of x with this mu prime, let's see what we get. Okay, so magical function, multiply it through. So magical that it turns this piece into the derivative of that magical function. Here's what is so clever about what we just did. This left-hand side is actually the derivative of the product of two functions. What two functions did I multiply together and then take a derivative of? So almost imagine like product rule backwards. What did you start with to get this as your product?
U of X.
Yeah, turns out we took the product of mu of x and y, and we took the derivative of that. So let's write mu of x times y. All right. Now, here's another beautiful part to this story. I see a derivative here, right? But at the end of the day, I know I reached my solution when I get y equals. So my life would be so much easier if I didn't have any of this stuff. I just had the y, right? How do I get rid of a derivative?
Integral.
Yeah, we integrate, right? So guess what we're going to do next? We're going to integrate both sides. All right, we integrated both sides. Now, because we have an integral and a derivative, by the fundamental theorem of calculus, all we're left with on the left-hand side is mu of x, y. And on the right-hand side, we don't know what those specific functions are, but we can integrate them later on. Okay. What is the last step for us to get to our solution? Like, yeah, we're gonna take that. We're gonna say, I wish you weren't over here. I wish you were on the other side. Then I could get my solution. Okay. So let's sort of review our story here for a moment. So we started with this first order linear differential equation. We knew it was first order because dy dx. We knew it was linear because we have coefficient functions that are only with respect to x. But the first thing we did was say, let's make the coefficient 1. That will make our life easier. So we divided away that a sub 1 of x. And for notation's sake, we renamed those correspondingly so that we could not have to write as much in our derivation, okay? And so to begin our story, we said, what if we had this magical function mu? And we multiplied through by mu. Okay, so multiply by mu of x. And then, because of the way we chose mu of x, we were able to use the product rule to rewrite that left-hand side. That allowed us to integrate both sides, and then we divided by mu. So the thing we multiplied through by, we actually divided away, so it didn't change our problem. Okay. So how we feeling conceptually here? Are we doing okay? Yeah, okay. All right. So then the question becomes, well, this magical function was all fine and good, but how do we choose this magical function? Okay. How do we find what this magical function is? Because that seems to be the key here, that if I want to use this method, I'm going to have to be able to find the magical function more precisely than just hand wavy, I found a magical function. Okay. So it turns out we're going to use this piece right here, all right? That mu of x times p of x is equal to mu prime of x. So to find mu of x, let's figure out where I'll give you a formula, but let's figure out where that formula comes from. Okay, so we know that mu of x, p of x equals mu prime of x. That's how we chose our magical function. So let me divide both sides by the mu of x. I'm going to get p of x by itself. So p of x equals mu prime of x over mu of x. And I'm going to go ahead and integrate both sides. Okay. So integral of p of x dx equals the integral mu prime of x over mu of x dx. And it turns out that this integral of mu prime of x over mu of x is u substitution, and then we'll end up with a natural log on that side. So we'll get the integral of p of x dx equals the natural log of mu of x. And there is a plus c here because we did integrate, okay? Now I know that yesterday I was like, we really don't need to have explicit solutions for everything, but there are some times when it's handy to. And so my question to you is, how can I solve this equation for mu of x? Because that's what I want to find, right? I want to find that magical function that I can multiply through. So how do I get mu out of the natural log? Yeah, I could subtract c, and then I could raise e to the power of both sides, exactly. Okay. And so we end up with mu of x equals e to the integral of p of x dx. Okay. This formula right here.
Plus c?
Actually, so that is one of those, we're still going to absorb all the constants at the very end. So in this case, we don't need that plus c.
Oh, thanks.
Yeah. So this right here, so important. Let's put a little bit of sunshine around this. All right. If you want to find that magical function, you have to find p of x first. And how do we find p of x? That's what we got when we divided that a sub 1 of x away. Okay. So let's see, I see a question in the chat. What did we do to get this? Well, I needed to get rid of the natural log. And so I'm going to do e to the power of both sides. And so the e in the natural log will leave me with just the mu. And then the other side, I'll still have e to the power of that side. Is that what you meant? Yes, okay. So when we're looking at these functions, I think a lot of the signs are going to come out when we divide those two coefficient functions, okay? And that will help us dictate whether we're going to get sort of a plus or minus here, all right? So we'll take care of that as we actually do a problem. But this sort of greater structure here is sort of two parts. One is find that magical function. Two, this is why that magical function works, okay? So let's try some examples, okay? Because again, I know that this sometimes serves as an example. You'll have professors that are like, yeah, I just did an example with you. This is an example. But I think we got to put some numbers in there. We got to put some actual functions in there so that we can see what's happening, okay?
Professor,
Yes.
there's a might have got buried is what happens with the absolute value on u of x.
Right, so the absolute value, what we're going to see is when we identify our p of x by dividing through, it's actually going to give us a sign for our mu of x. Okay, so it'll depend on our p of x, what we're going to get in terms of that absolute value. All right, let's try some examples, okay? Now, you do not need to do this next part, okay? Which is, I'm just gonna show us that this is to see whether we can separate it or not, okay? So if you wanted to check first to see if you could separate it, one thing that you might do is multiply both sides by dt, and we would end up with dv equals 9.8 minus 0.196 v times dt. And again, it's sort of like a highbrow phrase, but if we, using inspection, we can kind of tell that this dt is still going to be attached to a v. So we're not really able to separate all of the v dv's and all of the t dt's. And since we can't use separation, we might want to try a different technique, okay? And so when we're looking at this different technique, we want to match the format in that we had above, okay? And so what in particular, if we go back up here, what we want to do is find something of this form, dy dx plus p of xy equals f of x, all right? So in this case, I'm going to go ahead and move this last term over to the left-hand side, okay? And when I do that, I will get dv dt plus 0.196v equals 9.8, okay? If you were to put that in words, I would say make it of the proper form. So put equation into linear. Okay. Now, once you've done that, I think it is a good idea to, hang on one second. I'm just going to rearrange this. So sorry. let's just put this as step 1. All right, so step 1, we're going to put equation into linear form, and we did that by keeping our v dv's on one side and then the other stuff on the other side. Then my suggestion would be identify p of x and find mu of x. Okay. So according to what we had above, our p of x in this case is just the coefficient for v. So our p of x is 0.196. How do we find mu of x from here? Well, mu of x is that formula that we put that little rays of sunshine around. It's going to be e to the integral of p of x dx. And so we'll get e to the integral of 0.196 d. Oops, sorry, this should be dt, huh? All right, so it's that as our integral. Now, most of the time, the integral that you get here in the exponent is just going to be a basic constant one, maybe the power rule, or potentially like a very short u sub, but nothing too crazy happening up there, okay? And so when we integrate this, we end up with e to the 0.196 t. And again, we're sort of leaving the constant out right now because we know it's going to get absorbed in all of the other computations we do. Okay. So step 1, put it into linear form. Step 2, identify your p of x and find your magical function. We good so far? Okay. All right. Now step 3, we're actually going to take our mu and we're going to multiply our entire equation by mu of x. All right, so multiply our differential equation by mu of x. And so we'll get e to the 0.196 t dv dt plus 0.196 e to the 0.196 t times v equals e to the 0.196 t times 9.8. Okay, so all we've done is multiply through by that magical function. The hard thing is sort of sitting with that and saying, it's okay that it just got exponentially grosser, okay? Because things tend to clean up very quickly after this. We're going to rewrite the left-hand side. And in particular, we want to rewrite it as the derivative of the product of two functions. And so in this case, what two functions did I multiply and take a derivative of to get this? That's an important step to be able to do. So let's think about that for a moment. What two functions did we multiply and then take a derivative of to get that?
U of X and
I heard the last part. It is V. I'm having a little bit of trouble hearing you. I feel like it sounds like you're super, super far away. I'm not sure why that is. So that's okay if the technology is not, working. But yeah, that mu of t, right? And in particular, this is our mu. And so we're going to have e to the 0.196t times v. And we'll leave the other side the way it is. Okay. Now, we know that our next step now, that's okay. I'm sorry, I wasn't trying, we've all got, we've had to adapt a lot over this year, so don't worry about it. I appreciate your contribution. All right, so the next step is ideally, we want to solve for V, right? That's going to give us our solution. So how do we do that? We got to get rid of this d dt, and then we have to get rid of this mu. And so what we're going to do is integrate both sides. And a lot of times I won't write this. I will just show that we've got our mu times v equals, and I'll write the integral on the other side. So integral of 9.8 e to the 0.196t dt. Okay, so in some of my answer keys, you may see me skip this step because I know that I'm going to have a product. I'll have a derivative and an integral, so then I don't write that part and I just say, here's what I'm left with after I integrate both sides, okay? All right, believe it or not, we are one step away from, 1.5 steps away from solving this equation. So we need to integrate this side, and then we're going to divide by that mu. So when we integrate, we're going to get 9.8 e to the 0.196t. We'll do a very quick u sub, so we'll be dividing by that 0.196. And then now we can say there's a plus c, and that plus c takes care of all of the plus c's that came before it, okay? All right, so let's go ahead and isolate our v. The last thing we're going to do, we're going to divide through by this. And usually, but not always, some things will cancel out. Okay. And this first term actually ends up just being 50 because when we divide away the e's, and those reduce to 1, and when you divide away the other terms, you'll end up with, let me see if I can make this a touch smaller. You end up with v equals 50 plus c e to the negative 0.196t. All right. And for those of you wondering why we can't just combine this into a massive C, it's because we still have a T in here. It's sneaky, but there's still a T in here. And so that's going to change depending on time. So we can't just lump it in with a constant. We have to keep it separate. Okay. So let me go ahead and zoom back out so you can see the question on a single page, all right? So how are we feeling with this question? You know, putting some numbers to that process. Are there any questions coming up for us right now?
I am still really confused on the brackets part when you rewrite the left-hand side. I don't know how you go from that part to the brackets. Can you explain
Okay.
that?
Yes, I can. That is a very good question. So maybe let's imagine separately. Let's go back to Calc 1. So let's say I want to take the derivative of 5x squared times sine x. All right, so let's say I want to take that derivative. I would have to use the product rule, and I would get the first function times the derivative of the second plus the second function times the derivative of the first, right? So this is like my u dv plus v du format, right? And so what we're used to going in this direction, right? Somebody gives us two functions that are multiplied together and we say, take the derivative. But what we start to realize as we get into differential equations is sometimes the product form is actually less useful because we're trying to undo derivatives. And so if we're given something that is u dv plus v du, another way to write that is, hey, that was the derivative of the product of two functions. Okay. And so if we look over here, maybe it would be helpful if we wrote this one out. Let's see, e to the 0.196 dv dt. Oops. Plus 0.196. If we had this, and this was our u dv plus v, this must be our du, right? And so then we could write this as the derivative of u times v. Does that make a little bit more sense? Okay. Cool.
Thank you, that helps.
Okay. Yeah, product rule was so long ago and we always think about it in that one direction. But the reality is when we're starting to get back into all these ways of undoing derivatives, sometimes if we pack it back up, then we can just say, hey, integral and derivative, those go away and we're left with the function that we want, okay? All right. Shall we try another example? All right, we're going to use these same 4 steps. All right, so this will be kind of a good skeleton for us to think about. Put the equation into linear form, find your magical function, multiply through by that magical function, and then pack things back up using product rule. Okay. So let's take a look at example 2. All right. Now, example 2 has an initial condition, and we don't have to worry about that until the very end. Okay, so we're going to save that until the very, very end of the problem. And we will begin by saying, rewrite it so that we have it in linear form. Okay. And when we take a look at this, we've got x we're going to use y prime plus 2y equals x squared minus x plus, this is supposed to be 1 over x. So sorry, 1 over x. Okay, not minus 1 plus 1. That would have been silly. All right, so it's x squared minus 1 plus 1 over x. And when we have this, if we think back to that very first step, we wanted to make the coefficient of y prime equal to 1. All right, we didn't have to do that in the first example because it was already divided for us. In this case, we're going to divide everything through by x. Okay, and so when we divide through by x, we get y prime plus 2 over x y equals, let's divide each of these through, x squared divided by x gives me x, minus 1 divided by x gives me 1 over x, plus 1 over x divided by x gives me 1 over x squared. Okay, so let's just pause here for a moment to make sure we know where all of these came from, right? We're just dividing through by our a sub 1 of x. And now that we've got it in that form where we have the coefficient equal to 1, now we can start to think about, let's find our p of x, let's find our mu of x, okay? All right, so we've got a lot more letters this time. What are our thoughts on p of x? What do we get for p of x?
Is it 2 over x?
It is 2 over x, exactly. That p of x, and let me just make sure I'm using the same color here. That p of x is the coefficient for y. Okay. Now that we've identified our p of x, we can find our mu of x. So mu of x is going to equal e to the integral of p of x dx, which gives us e to the integral of 2 over x dx, which is going to give us e to the 2 natural log of x. All right, we good so far with the derivatives? I mean, the integrals. So 2 over x is going to give us that natural log, like, and then the 2 is that constant. So we'll just keep that in the front, 2 natural log of x. Now, we want to try and avoid having like, is it plus, is it minus as much as possible? And one of the ways that we can do that is think back to our log properties, where the coefficient actually represents the power of the thing that you're natural logging. And so we actually have e to the natural log of x squared here. And because I'm squaring the x and that's always going to be positive, I no longer need my absolute value signs. Okay. We can even simplify this one step further. E to the natural log, those undo each other. Oh, that's not what I wanted to do. My bad. Come back. Okay, so sorry. Let's try this again. So what can we do to, oh, it didn't even pick up that last piece. e to the natural log of x squared. That e and natural log undo each other. So it turns out that our magical function here that we're going to multiply through by is just x squared. Okay. So one of the things that I think is very beneficial is all of the algebra that we did to simplify means that we're going to have a much less complicated multiplying factor. And the less complicated that is, the easier our life is going to be when we try and unpack everything into that. Okay. All right, let's multiply by our mu. All right, let's multiply our original differential equation by mu. So we're going to go to this version, the one where we divided through by that eighth of 1. And I'm going to take every single term and I'm going to multiply it by x squared. So x squared y prime plus 2xy equals x cubed minus x plus 1. Let me pause there for a moment and just make sure we know where all of those terms came from, and is that accurate? Okay. So we've multiplied everything by mu. Now, what should happen is we should be able to rewrite that left-hand side, okay? This left-hand side should be the derivative of some product. And it turns out that we've got u is x squared and our v is y. Okay. Once you've got that, you are in the home stretch. We're going to integrate and then we're going to divide by x squared. So x squared y equals the integral of x cubed minus x plus 1 dx. And I'm not writing the integral sign on the left-hand side because that cancels with my d dx. This will give me x squared y equals, oh, thank goodness, just power rule. None of the crazy stuff we were looking at yesterday. X to the 4th over 4 minus x squared over 2 plus x. Now we need that plus c, okay? All right. If we did not have initial conditions, we would be done. We do have initial conditions, so we want to find a number for c so that we can write our whole answer with like the x squared y equals x to the 4th over 4 minus x squared over 2 plus x plus a number. Then we'll know we're done, okay? So let's plug in our initial conditions. That'll be sort of like a step 5. That's not for every problem, but you may need that initial conditions if you have them. And if we plug in those initial conditions, we're going to get 1 everywhere we see an x, a 1/2 everywhere we see a y, 1 over 4 minus 1 over 2 plus 1 plus c. Then we should get to a point where the only thing we don't have is that constant. And then with a little bit of of computation, we get 1/2 equals, let's see, this is negative 1 1/4 positive 3/4 plus C. And then we'll get C equals negative 1/4, I believe. Yeah, okay. I feel like the more math I do, the worse my computation gets. So please double check me because sometimes it doesn't come out right. This would be absolutely fine to leave in explicit form. It's also not too much harder to make it into an implicit. You would just divide by that x squared. So either way is okay here, but we'll just rewrite this all so that we have, instead of a plus C at the end, we have a negative 1/4. Okay, so you got the whole problem on one page here. How are we feeling about this example? We layered in a few more steps. Okay, I've got a thumbs up, that's good. So far, so good. Okay. All right. Well, let's go ahead and try a couple more examples. Let's see how many we can squeeze in. I always find that more examples are helpful. So let's take, yes, sorry, go ahead.
For this one, if you went ahead and put that in explicit form, doesn't that simplify quite a bit more? And then your C is gonna like kind of become something different, right?
Yeah, so the C is still just the constant though. So this would be 1/4 and then maybe like 1/4 x squared. That x squared is not technically part of the constant, but I know what you mean. Like the last term would be different.
Yeah, because that negative x squared over 2 is gonna just become a negative 1/2, right?
Exactly.
And then you add it to the 1/4. But
Oh,
do you
no.
want it in this form?
Okay. I see what you're saying. You have to divide everything here by x squared, including that negative 1/4.
Oh yeah, I see. Sorry. Yeah, thank you.
You're fine. So this, and I should write these out more instead of just telling you that it will reduce, but if you wrote this, that would be okay. Like if you divide everything through by that x squared, as long as you also do the constant, then you're good to go.
Okay, thank you.
Okay. Both are okay. All right. Let's try a couple more. Boop, boop, boop. All right, so example 3. We've got dy dx plus y equals x. And we have an initial condition, which means we're going to need a step 5 so that we can plug that in and get a number for c. Okay. So is this already in linear form? I do a quick glance and I say yes, because I have my dy dx plus, actually, you know what I'm going to do? Okay. For those of you who are using LaTeX, in case anyone is planning to type this, I know that it is a little bit more work to type in a fraction here, okay? So if you're feeling like I've typed in too many fractions, if you change this to a y prime, that is fine with me, okay? So if you want to change that to a y prime when you're typing it, that is okay. Otherwise, if you want to type in LaTeX for a fraction, you'll need \frac, and then the first set of curly braces will give you the numerator. Yeah, and the second will give you the denominator. Okay, so if you're looking to type in LaTeX, the frac is not too bad, but if you're going to keep typing it all the time, it is also a time saver if you just type in y prime, right? So I'll leave that up to you in terms of how you choose to do that. But either way, we can see that this is indeed in linear form, and we don't need to divide anything because the coefficient for our dy dx is already 1. So we can jump right to step 2, where we're going to find our p of x and mu of x. Okay, so if we're finding our p of x, it's going to be the coefficient of the y term. And so in this case, it might look like we have nothing there, but we have that invisible one, right? We have that invisible one. And so that's something you want to be careful of, that p of x is not going to be 0 because I have a y term. There has to be a coefficient there. Mu of x will give me e to the integral of p of x dx. And that will give me e to the integral of 1 dx. And that just gives me e to the x. All right, so this integral to find your mu of x, not too bad. Much less simplification than the previous problem, right? But now we're ready to multiply through. We're going to multiply through by that mu. And I believe that sometimes mu is referred to as the integrating factor. So if you see the term integrating factor, they mean mu, okay? So we multiply through, we get e to the x y prime plus e to the x y equals x e to the x. Okay, so far, not too bad. Now at this stage, if we found our integrating factor correctly, that left-hand side, we should be able to pack it up into a derivative of a product. Okay, that's a good way to check and make sure that you're headed in the right direction. So left-hand side, this left-hand side turns out is the derivative of e to the x times y. And that's going to equal x e to the x. Okay. Now we have to integrate. And when we integrate, that d dx is going to go away, and we're only going to have e to the x times y on that left-hand side. All right. So the front end of this problem, not too bad. The back end, oh, is going to be a little bit trickier because what method do we need to integrate that right-hand side?
Integration by parts.
Yeah, we're going to need to do integration by parts, okay? And a good way to tell that you're going to need integration by parts is that you have two functions that are different kinds of functions multiplied together, right? So like an x and an e to the x, an x and a natural log x, a sine and an x squared, okay? And there's lots of different ways of doing integration by parts, but if we sort of use this as a chance to review the formula from yesterday, we know that integration parts, we have the integral of uv minus the integral of v du. And so we need to find our u and our v from the problem. Let's actually write the other side of that as well. So the integral of u dv equals uv minus the integral of v du. So our U in this case and our V, it's so important to choose our U carefully. Yesterday, I gave us the phrase lipet. Right? Anytime you see a log, that is absolutely going to take priority. Next up in line, any inverses, and then third in line, any polynomials. I see that I have an x, so my U is going to be x. That means that the other part is my dv. I take the derivative of x, I get 1. I take the integral of my dv, and I get e to the x. We'll plug all those into our integration by parts formula, and we end up with x e to the x minus integral of e to the x dx. So that gives us e to the xy equals x e to the x minus e to the x. And now I'm ready for that plus c. Yay. I would say that if you have initial conditions, it's probably nice to leave it in your implicit form, plug in your initial conditions, and find that C value, okay? If you get a different C value than someone else, it might be because you did it in a different order. And so you've compensated at different points along the line, but ultimately, if you simplified it, you should both have the same answer. It might just look different from the first view. So initial conditions, what do we have? Whoops, we have y of 0 equals 4. And a lot of times these initial conditions make a lot of the messy looking things actually, they turn out to be nice numbers. So for example, everywhere we see an x, we're replacing it with a 0, which means a lot of things are going to turn to 1. Okay. So e to the 0 times 4 equals 0 e to the 0 minus e to the 0 plus c. Let's see what cleans up here. This goes to 0, this goes to 1, this also goes to 1. So I've got actually 4 equals -1 plus c. Right, so even though our solution, the general form of it, looked kind of gross, because of the initial conditions, like just the idea of plugging them in, a lot of things actually made for a very nice C value of 5, okay? And so when we go ahead and finalize our solution, we'll get e to the xy equals x e to the x minus e to the x plus 5 would be an absolutely fine way to leave it. And if you wanted to divide through by the e to the x, you could do that as well. And you would get y equals x minus 1 plus 5e to the -x. This would also be okay.
The second way of writing that, that is implicit or explicit?
That one would be explicit because I
Okay.
have it as y equals explicit and implicit. Yeah. All right. So we've taken a look at 3 examples so far. And we have, let's see, we have 2 more to do. I'm not sure that we'll get through both of them. My thinking right now is let's do example 4, okay? Let's do example 4. So example 4, very similar to what we've done here, all right? We're gonna use those same few steps, and I think the integrals are not too bad, maybe a little bit of use up, all right? The last one, I do just want to show you that sometimes we can actually use 2 different methods to solve the same problem, right? And typically that's sort of like a nightmare situation for some of us. We're like, oh gosh, we can use more than one method. Which one should we use? And so I thought this was a good exercise to think about. What if we use separation of variables? What if we can use this with an integrating factor? We know that we should get the same answer. And so this could be a good exercise for you to try on your own to make sure you've got both methods pretty down pat, okay? You'll be able to, I feel we're pretty good with the separation of variables. So once you know that answer, using the integrating factor, you should get the same answer, okay? So that being said, let's take a look at example 4. And we have 2y prime plus 6y equals 3. Do we need to do anything before we find our mu of x? I see some heads nodding yes. What do we need to do here?
Should divide everything by 2, right?
Yeah, so to get it in that form that we want, we're going to go ahead and divide by 2. So y prime plus 3y equals 3 halves. Okay, so I just divided by to make sure that coefficient for my y prime is 1. Got to find our p of x and use that to find our mu of x. In this case, p of x is just 3. Right? 3 is our coefficient function for y. We plug that into our mu formula, e to the integral of p of x dx, we'll get e to the integral of 3 dx. And that integral is not too bad. We get e to the 3x. Okay. So e to the 3x is going to be what we multiply everything through in our next step. So I'm going to go back to my coefficient is 1 variation, and I'm going to multiply everything by e to the 3x. Now at this point, I tend to pause and just look at that left-hand side. Make sure I can see a u dv plus v du, right? If we have that, that is a confidence booster that we are headed in the right direction. And it looks like we have u dv plus v du, right? And we actually are really grateful that there's a 3 here, 3 e to the 3x, because if we didn't have that 3, it wouldn't actually be our du, right? We have to remember that chain rule piece when we take that derivative. That's where that extra 3 comes from. I can write the d dx of that product. If I were to skip that step, it might look something like this. E to the 3x times y equals the integral of 3/2 e to the 3x dx. Right, I'm going to go back and fill in that step right now, but I don't think that I necessarily wrote this out in my answer keys, this middle step. All right, so that's just why I want us to know what happened in between. All that we're missing is that d dx of that product will equal the right-hand side. Okay. So especially as we're getting into longer problems, thinking about where you feel comfortable skipping a step, I think it would be okay to say, I didn't write that step because I knew it was the product and I knew I was going to integrate. Okay. Now, luckily, I think that we've just got a very straightforward u sub situation for our integral. No integration by parts, no partial fractions, just a little u sub. And so we'll get e to the 3xy equals 3/2 times 1/3 e to the 3x plus c. And you could certainly skip that and just say it's going to be a coefficient of 1/2, Judy. I know that 3 divided by 3 goes away. That would be fine as well. And let's see what we've got. We've got e to the 3xy equals 1/2 e to the 3x plus c. Now we don't have any initial conditions, so we don't need a step 5. We could call it a day here. And we could specifically call this our implicit solution. If you want to solve for the explicit, you could divide through by that e to the 3x, and you'd get 1/2 plus c e to the negative 3x. And this would be our explicit solution. Okay. I think in the answer keys, I typically leave them as implicit. So if you get to this point, you should be able to match what I have on an answer key. Okay. And if you choose to go further, I trust you to do that algebraic simplification. All right. How we doing here, folks? New day, new method. Tomorrow's another new day with another new method. Welcome to summer school. All right, so we're going to stop here for today. I'll give you your extra 7 minutes on the back end so that you can take a look at example 5, just kind of use that as a refresher and make sure you've got that separation of variables and that integrating factor. You know your answers should match. So once you've got one, you know what you're aiming for in the second one, okay? I still see some people writing. Is there a slide or a page that people would like me to go back to, or are we okay? You're okay, all right. No worries, no worries. All right, I'm gonna stop sharing my screen then, and I'll go ahead and post these notes right now. So the notes will go up, the video takes a little bit longer to render, but our class is not 2.5 hours like my Calc 1 class, so the videos render a little bit faster. I know, poor things. 7 a.m. and 2.5 hours, Monday through Thursday. Okay. All right, so have a great rest of your day. There is a discussion due by the end of today. So if you haven't gotten to that yet, make sure you go back and do that. Then the homework is due on Saturday and discussion 2 is due on Saturday as well. Okay. All right. I'll see you folks tomorrow. Have a great rest of your day. Bye.
Thank you, Professor.
Thank you.